Okay, with that, we're going to move over to Dr. Edwin Ritchie. Most of you on here already know Dr. Ritchie. He's a soil extension scientist. Does a really good job. Has done a lot of work with manure management as well. Really important topic, particularly in Western Kentucky, and taking those products and making them a viable fertilizer option for a lot of our fields. Edwin's done a lot of really good work since he's been here as faculty, and so Edwin, we really appreciate you being on, and I'll let you take it from here.
All right, can everybody hear me? I'm going to take that as a yes and move on. So today I was asked to speak about soil sampling, and thought I'd bring in, if we had a little time, about how the fertilizer recommendations are developed. So the critical part of soil testing and soil sampling is getting a good sample. Anyone that's heard me give this talk before remembers how much I focus on that representative sample. There's roughly 2 million pounds of soil in an acre furrow slice. So that's 1 acre. If we're looking at a 10-acre sample, that's 20 million pounds. Of that 20 million pounds, we're only looking at about a teaspoon for your P, K, and your other bases, and 1 tablespoon for pH. So that pint box or bag that you fill up really needs to represent that area that you're trying to get a good value on to make a good sound fertilizer recommendation. So what we look at are uniform areas. We base that on drainage, cropping history, erosion, a lot of the things that Hannah and Sam talked about earlier. If we have a 20-acre field and 3 acres in the middle of it grew tobacco, that 3 acres is probably going to be different than the other 17 acres out of that 20-acre field. So to get a uniform sample, a soil probe is by far the best tool to use. Some people might want to use a shovel. You can use a shovel, but you need to make sure that you have the same thickness, same width from the top to the bottom. If you're taking a 4-inch sample and it's 4 inches wide at the top of that sample at the soil surface and only 1 inch wide at the bottom at 4 inches, then you've skewed that data or that analysis towards the top. So you need to make sure that it's a good representative sample. We don't want to use galvanized buckets that can contaminate our sample with zinc, so a good clean plastic bucket. And then I like to air dry it. Just gives, you can crumble it up a little bit better, get a better representative sample to put into that bag to send off to the lab, and then put it in the appropriate bag, label it, and send it off to the lab. So we recommend no more than 10 to 20 acres per sample, and that really depends on the variability inherent to that field. So this is a farm that my family actually purchased about 25 years ago. It joined up to the family farm that my grandparents bought back in the late 30s. And
hey, Edwin.
Yes.
We don't see the picture of the farm.
You don't see the picture of the farm. How about now?
Yes.
All right. Thanks for letting me go for 4 minutes. Thanks for catching that, Hannah. I guess I didn't hit share. I did hit it, but it didn't take. So anyway, here is a picture of the family farm. There's roughly 15 acres in this area. This blue shaded area, well, let me back up a minute. This was a dairy farm for about 40 years. So this blue shaded area was where the cattle stalled before coming into the milking parlor. This has since grown up since we took this picture, but right in here was the milking barn. So they stalled in here, they'd come in, go into the barn, come out, and leave. So of that 15 acres, there's roughly 4 acres that had a lot more manure than the other 12 acres or 13 acres or 11. So if we would have used this area and included it with this 15 acres, we're going to elevate our soil test results, which will likely decrease our soil test recommendation. So this area here should be separated from the rest of the 15-acre field. So that's one type of variability to consider. Now here's another one. This is just an example. I used a 120-acre field. Each of these squares represent a 2.5-acre grid. Now we have 2 options within that 2.5-acre grid. This top option has high, medium, low all through that. It works out to a medium if you do the average, but you go from a high to a low to a high to a medium. So there's a lot of inherent variability within this small area, or you can have, you know, more uniform area within that 2.5 acres. Hopefully, for sake of management, we're looking at this bottom example. It makes it a whole lot easier to manage. So if we look at the bottom example, now I have it over here to the right. Hopefully we have something that would break out like this. So we have zones that we can look at. We have a low testing zone in one area of the field, maybe a high testing zone and a medium. So now I have potentially 3 different management zones I could separate and manage differently. So that's one of the examples where it shows intensive sampling can help with your management decisions. This is real data. This is a project that was funded by the Kentucky Soybean Promotion Board. This is the second year. This is the first year of data. We managed this, or the farm managed this, I don't know how long prior to me taking it over, but for a long time. So this was managed as a uniform production field by the farm. If you look, we go from 207 to 177, a low of 151 pounds of soil test K per an acre, to a high of 269. And if we look at it, kind of averaging it across this way, through this row, we had 175 pounds per acre. Our recommendation averaged to 70. Same thing here, as a mess up with the sampling here, 60, 70. Now, if we look at it this way, we see similar variation, but we do see a spot here where we have a recommendation of 70, 80, 70, 80. So that right there might pop out into a different management zone, but then it comes back to scale. So if this was a 20-acre field, I would probably break this out into a different management zone, and then we would have different, we would have another one where we'd probably have to add a lower amount of fertilizer because it has higher soil test values. However, these are small plots. This is a 10 by 50 plot, another 10 by 50 plot. So this whole area right here is only about 3/10 of an acre, or 36 hundredths of an acre. So even though we had this much variability within a small area, it shows what you would see and most likely in most fields that are being used for production ag. The other thing that I'd like to point out that comes back to Sam and Hannah is, even though we manage this the same, we have things that were influencing these different soil test results. We had soil test results that were lower in this area here and higher recommendations. that over time, year after year after year, was probably removing higher yielding, removing higher rates of nutrients, and we were applying that flat rate across the whole field. So all this comes into making our different soil test recommendations. Out of that same field, this was a soil fertility trial. We had band or no band, and then we applied the UK rate plus 25% or minus 25% compared to our check. So we were in that medium range, the low end of the medium range, but we really didn't see a whole lot of difference in our yields. It went from 45 to 48 to 47 to 50. No statistical differences between yields at this rate. That means we're applying enough even at our low rate to maximize yield in this environment. We did see a slight increase in tissue, potassium tissue content, but really nothing to get excited about. It did show that we had a little bit more uptake with our added fertilizer compared to the check, but nothing really big and nothing that resulted in the yield increase in this environment. So back to collecting a soil sample, how many do we need to collect? Well, it depends, but generally more is better. For this procedure, this practice, I'm looking at randomly collecting them across the field. I would say a minimum of 10, but 20 is probably going to be better. However big the field is, the more you can take, the closer to reality you're going to get with that sample size. And again, make sure you mix it in a plastic bucket and avoid the contamination with the galvanized zinc. Here's my little $3 bucket. I've probably had over 2 or 3 tons of soil in that bucket since I've started 10 years ago. I use it a lot. It's easy, cheap, easy to clean. Take my samples. I like to crush them if I have the time, if they're not too wet. And then I have a nice powdery stuff that is homogenized when I pour it into the bag. So if I happen to take more than the bag needs, I'm not getting a big core versus leaving one. I've mixed it. So I've mixed it across the core. Again, a little bit better representative sample of that area. So when do we collect the sample? Well, doesn't really matter a whole lot. Fall versus spring, they differ some. The bigger thing is to watch that trend over time, and you want to collect it at the same time each year so you can watch those trends. This is some work that Lloyd Murdoch did. It's a AGR publication, but this first figure 1, it shows what our typical soil pH would do as a water pH. As we went from spring into summer, into fall, it dipped and then came back up. Well, we have a low pH here in the middle of August. We have dry conditions present. So our plants are pulling water and fertilizer salts from depth, putting it at the area where the plants can use it. That fertilizer salt is going to help displace hydrogen, which is going to result in a lower pH. Now, Frank Sikora was aware of this, and he made an adjustment. All you agents out there, I'm sure, are well aware that we now do a salt pH. That salt pH helps reduce this big fluctuation in pH due to moisture content. But regardless, we want to take it at the same time every year, very similar, so we're looking at that same type of response. Here's potassium. It drops, it goes from a high, drops down, and then starts going up somewhere around black layer. So what's going on with potassium? Well, potassium is very mobile in the plant. It's easily leached out of the plant. So as the plant is utilizing it, taking it up, utilizing it, incorporating it into the biomass, and then we start start to senesce. As the plant starts to senesce, the leaves start dying, it rains, it's leaching this potassium out of the leaves back into the soil. So it goes down and it goes back up. So again, if we're looking at a sample at July versus March, they could differ greatly. So we can avoid a lot of that by just taking the same sample, or taking that sample at the same time year after year, and then looking at our trends. So how often, and that's really specific to the crop, higher the value, the greater the removal, the more intense sampling. You're looking at $7 a sample plus the time. So let's just say you have $10 per sample in it, and it represents 10 acres. That's $1 an acre. What other practice do you do in your farming operation that costs less than $1 an acre? So that's money well spent, provides a great amount of guidance, so you can make sure you're not over or under applying your fertilizer. So the high value crops, dark and burley tobacco, high removal and high value alfalfa, high removal silage corn or grain, small grain baleage. So these crops would benefit, or your yields and your management would benefit from more intensive sampling with these crops versus the others, like a corn soybean rotation. You can get by every 2 to 3 years with that and apply accordingly. So what's our sample depth? Well, it depends on tillage. For the University of Kentucky, the work that was done years ago, and it still holds true, we're looking at a 6-inch sample, or to the depth you till, for a tilled system, or a 4-inch sample in a no-till system or a pasture system. If you're looking at minimal tillage, like a turbo till where you're disturbing the soil 1 to 2 inches, I would still go with that 4-inch sample, because you still have the stratification of the nutrients. So that's the best approach with that. This was a little thing I did for the cat school a few sessions back. It really pretty neat, and it really surprised me how much we saw this. But I had 2 fields. One of them was a Kreider silt loam right across the road, and then we had a Zanesville silt loam on the backside of the station. Both rotations were either corn soybean or corn wheat double crop beans. We had no-till, so we should be sampling to a 4-inch depth, and I just laid out an area within the field, a 5x5 square. So we had 4 spots within that 5x5 square. This was roughly a foot, another foot. So I sampled 12-inch sample, 12-inch sample, 12-inch sample, 12-inch sample. Then I took 2 6-inch samples, 2 6-inch samples, 2 6-inch samples, 2 6-inch, and then 3, 4, and so on. So I tried to collect similar volumes, but it was from a very, very small area within a field. Remember, from this corner to this corner, we're only looking at a 5-foot square. So very, very small area. So does soil test depth really matter? If you look here, 0 to 1, 0 to 4, 0 to 6, 0 to 12 for phosphorus. As we increased our soil depth, our soil sample depth, we decreased our fertility level. Same thing for potassium, go from about 1,000 to 600 as we increase with depth. Now that's on the Kreider. That's tremendous fertility. I don't know exactly what happened before we took this over, but wow, you could just about sell this soil for fertilizer, at least a top inch or 2. Now the Zanesville, it's a little bit different. Same sample depth, but now our soil test phosphorus started at 90 if we just looked at the 1-inch. Now a 4-inch, which is the sample depth we should use for this rotation, 45, down to 32. And when we go down all the way to 12 inches, we're looking at 15. So there's a pretty big difference there. Soil test potassium, same trend. So does that really influence our management? Well, it depends. On this crider, we're above that critical threshold that we would expect to see a response. Therefore, our recommendation, regardless, is 0. Even though we had a huge difference in soil test values, we're above that critical value. With the Zanesville, however, it does matter. It went from 90 to 45, so a 0 recommendation to 40. If we go deeper, now it's 70 to 100. So depending on what that soil depth is, we might either be under applying our fertilizer or over applying. Same thing is seen for potassium. So soil test depth does matter. I'm going to skip through this real quick and get to the last part and just kind of reiterate what we were talking about. So does our soil test matter, or our soil sampling matter? Yes, it influences it a lot. We have the uniformity. We need to make sure that sample is representative of the area we're trying to evaluate. Remember our soil test depth, 4 inches for no-till, 6 inches for conventional till. Try to keep those samples small. You know, a 10-acre field is probably going to be better represent that field than a 20-acre field. But when you start getting above 20 acres, there's so much variability that you don't know what you're looking at. And how often? Generally, the better, the more often you can, the better. But for sure, the higher the value, the higher removal. You know, look at an annual or every other year, just because it's such a cheap and useful operation that can lead to a more profitable enterprise. So that is what I have, and I believe I stayed on time, and I will be happy to answer any questions at this time. Thank you, and Hannah, thanks again for letting me know my slides weren't showing.
Thank you, Edwin. We appreciate you getting in there and talking about that. I think showing those differences in how the soil test values change when you're doing those different depths. If nothing else, everybody should be questioning if they're not pulling off their own soil samples. They need to be questioning how their soil samples are being viewed. Okay, next up, I just mentioned one researcher with Monty. Next up is another one of our colleagues who has a primary research and teaching appointment, and that's Dr. Hannah Poffenbarger. Hannah really works in soil and nutrient cycling, soil carbon cycling, and she's doing a lot of work in the cover crop area right now as well. And so, Hannah, we appreciate you being part of our field day, and welcome to the program.
Thank you. All right, everybody can see my slideshow, okay? All righty. Well, thank you all for being here and tuning into the field day. I'm here with my graduate student, Sam Leithold, and we're gonna talk today about a project we've been working on in collaboration with Ola Wendroth and also Matse Samran, who was just presenting. And the project relates to understanding and then trying to address and manage spatial variability in corn yield. So there's 2 types of variability, thinking about variability in corn yield. The first is temporal variability. That's just the variation that exists from one year to the next. And then there's the location variability or spatial variability. And so the year-to-year variation can be driven by overall trends in corn yields over time, which we generally see positive trends over time due to improved genetics and better management. But we can also see deviations from one year to the next just based on favorable or less favorable weather conditions. And then, of course, the location-to-location variation can be driven by management, how different fields are managed, but also soil and landscape properties that can affect resources that are available to the crop. And then I've drawn these two circles as overlapping because we often see an interaction. So we see an interaction of landscape position and weather on corn yields. And so, for example, we can see in a dry year stress occurring on the slope, the upland positions where the corn might be more water limited. But then in a wet year, we may see lower yields in depressional areas where the crop is impacted by excessive water. And so because we can't predict weather very well in advance, it can pose some challenges because it's hard to predict then what the spatial pattern of the yields might be at the beginning of the season when it's time to plan out how you're going to manage the crop. So we'll talk a little bit about some of the processes behind this variation and then present some research results. So this is kind of a general hill slope diagram that soil scientists use. So we have at the top of the hill, the summit, that convex position is the shoulder that transitions into the back slope, the most sloping part of the hill slope, which transitions into this concave portion, the foot slope. And then the toe slope is the lowest elevation and low slope area in the hill slope. And so just based on studying a few hill slopes in Kentucky, I have some average properties we might expect. So you can see the elevation changing by about 7 feet going from the top of the hill to the back slope and then down to the toe slope. And in general, those summit and toe slope positions are lower slope, and then the back slope is the most sloping part. And so in a cropped field, obviously, there's a limit to how sloping it's really going to be. So this is sort of typical of the rolling cropland we might see in Kentucky. So one thing that can vary along the hill slope is the soil depth, and that relates to the rates of soil formation and erosion. So on the back slope, you tend to have the highest rates of erosion, and so there's not a lot of soil that generally accumulates there. So it may be shallow soil to the bedrock. In the hill slopes we were looking at, it actually got as shallow as about 8 inches on that back slope position. And then in the toe slope, you have the accumulation of topsoil that is moving downhill from the back slope area. And so you tend to have the deepest soil in the toe slope position. You can also see variation in soil moisture. So this was just some measurements from soil samples we had taken in the fall, and typically find that the toe slope is a little wetter than the upland positions, in part because the water after a rainfall event is running downhill and accumulating there, but also since it's lower in elevation, we may see a slightly shallower seasonally high water table, so closer to the surface. And finally, the organic matter levels can also vary, and we typically see that the toe slope, again, is going to be the most enriched in soil organic matter. Again, you have the accumulation of topsoil that can be eroding from uphill, which tends to be enriched in organic matter. And you can also have slightly slower decomposition taking place where you have a little bit wetter conditions on average. So in general, we tend to see that most soil resources are available at the bottom of the hill, which kind of makes sense, but also at the bottom of the hill, it's the area that's most prone to excessive water. So we wanted to do a study to look at these spatial patterns if we can really expect to see the spatial patterns changing depending on weather from one year to the next here in Kentucky, or if they remain relatively consistent, and which would help with being able to manage according to that variability. And so we had 2 sites picked out, one in Glendale and one in Lexington, and we identified hill slopes within these fields. And so you can see here in the Lexington site, we had plots laid out in the summit, the back slope, and the toe slope, and that back slope is showing the highest slopes, as you might expect. And then in the Glendale field, we had actually 3 separate hill slopes, and that's what those small boxes represent. And these are some pictures of those sites. So in Lexington, you can see we laid out those plots within a grassed field. So there are some grass areas between the plots. But here we have the toe slope at the base of the hill, the back slope, and then the summit is behind where I was taking the photo. And then in Glendale, in this photo, we're looking uphill, toe slope, back slope, and summit. And you can see that there was some redistribution of crop residue that happened during a heavy rain. So there's another way that the toe slope can accumulate organic matter. But one of the other features of this study was not just the landscape position, but also the presence of a cereal rye cover crop, because we wanted to know if having that cover crop could help to reduce the spatial variability by helping to conserve water on the back slope and summit, where water can be more limiting due to the shallower depth, lower organic matter. And so here's a couple of photos from the studies during corn growth, and you can see in Lexington on that back slope position, the corn was looking more brown. And so right around this time of year, last year, we started to see a lot of stress showing up, a lot of water stress on the back slope. And then the Glendale site, you can see we did have some lighter green areas because embedded within this study were some different nitrogen rates. But we're going to talk today just about the adequate nitrogen treatments and really focus on the response of corn to the landscape position and cover crop. So at this point, I'm going to let Sam talk a little bit about some of the results that we've found.
Thanks, Hannah. Good morning, everybody. We'll start by looking at the data from the field trials in 2019. And as you can see from this figure, it's a year during which we had a little bit below average rainfall and above average temperatures. There are a few things that stand out. The first is that landscape position was a major driver of yield at both our Glendale and our Lexington sites. We saw that the toe slope areas down near the bottom of the hill yielded higher than both the sloping and the summit positions. At Glendale, the lowest yields were in the summit position, while at Lexington, they were in the back slope position. And when we look at our soil water storage, the total amount of water within the soil profile at our Lexington site, we can see that part of the reason why this back slope yields were so low. Right? Throughout the growing season, there was significantly less water in the back slope position compared to the summit and the toe slope. And while we don't have the same data for our Glendale site, based on our observations throughout the season, it seems that landscape controls on soil water distribution played a major role in dictating yield there as well. And now when we look at the cover crop treatment at both sites, we see no significant difference between the rye cover crop and the winter fallow, although there is a trend towards lower yields following the cover crop in some of the landscape position. The landscape variability across our replicates and across these hill slopes was really high, and it may have drowned out a significant effect of the cover crop. But when we look at soil water storage at the different landscape positions and how the cover crop affected that, we see a small but significant increase in soil water following the cover crop compared to the fallow across all 3 of our landscape positions. And so with these observations, no significant effect of cover crop on yield, increased soil water under the cover crop, and significant variability between our landscape positions when we have average rainfall conditions. We asked this question of what are the effects of landscape position and cover crop under different kinds of weather? And to look into this, we divided the last 30 years of weather data into 3 categories based on rainfall: dry, average, and wet, and then compared yields between these categories. And so to do this, because we don't have a time machine, we took the data from our Lexington site in 2019 and used it to calibrate a dynamic crop model, the Decision Support System for Agro-Technology Transfer, or DSAT, and ran it under different weather scenarios from the last 30 years. The power of this tool is that we can put in all of these different inputs that we measure in the field, like soil texture and soil depth, and crop characteristics like time to anthesis or the number of kernels per ear, in our management activities. And after we get it running right, we can use it to look at things that we don't have the time or the ability to measure, like soil evaporation or soil drainage or daily nitrogen use by the crop. And so when we look across the 30 years of simulations, it becomes clear that 2 things overwhelmingly drive the majority of variability in this rolling hill field: weather and landscape position. And so what we're really seeing is that in our region, yield stability is primarily controlled by a combination of that year-to-year temporal variation. You can go to the next slide.
Oops.
No problem. That year-to-year temporal variation and that location-to-location spatial variation that Hannah mentioned in her first slide, but not the interaction between weather and landscape position that might be observed in a less well-drained soil, like something in central Iowa. And so when we look at these 2 factors separately, starting with landscape position, on average, across the 30 years of simulations, we see a yield penalty of 76 bushels per acre when we compare the back slope and the toe slope, a pattern similar to what we observed in 2019. And then when we look at the weather categories, we see that dry years are really where we're losing a lot of yield. Across the landscape positions, we see a 77 bushel decrease in yield when we're in the bottom third of that distribution of cumulative rainfall during the growing season. And so combining these factors now, we can see that the different landscape positions react differently to different weather conditions. The toe slope always yields the most, and the back slope always yields the least, no matter how much rain we got. But the biggest increases in yield with increasing precipitation were on the back slope. Even after the summit and toe slope became relatively stable with increasing rain, the back slope continued to yield more as we got more precipitation. And part of that is the limited soil water storage that we observed in our field trial. And when we look at how many years out of that 30-year period that different landscape positions experienced a yield loss greater than 10% due to water stress, we see that the back slope position was far and away much more sensitive to water stress than our other 2 landscape positions, experiencing water stress in 17 years out of the simulation compared to 6 years in the summit and toe slope. So now moving to the cover crop aspect, similar to our field observations, the model showed no difference in yield between cover crop and fallow in 2019. However, when we look at the driest year of our simulations, highlighted in that red box, we saw a yield benefit from the cover crop, especially on the back slope position. In fact, we actually saw that the number of years that the back slope experienced a yield loss due to water stress decreased when that corn crop was following a rye cover crop. And so what seems to be happening is that having residue there from the cover crop during a dry corn season increases the surface roughness and makes it harder for water to run off from that sloping position. It decreases the likelihood that water will pool, and it increases the percolation down into deeper soil layers. And then it also decreases the soil temperature, which reduces the amount of water leaving the soil surface through evaporation. And all of these processes working in tandem allows for more water during the corn, or for the corn, during critical growth phases, like flowering and grain fill, and reduces water stress and that year-to-year variability. So overall, just to sum up, our model results indicate that the addition of a rye cover crop increased available soil water making yields more consistent over time and space. And when we look at the distribution of yields across our landscape positions and our 30 years of weather in this plot here, we can see that the green curve, the cereal rye treatment, is narrower and less variable than the brown fallow treatment behind it, while having similar yields, those dashed lines, which are just 5 bushel difference. So.
All right, thank you. And I'll just wrap up this presentation with the takeaways. And that is that we found that the corn yield variability was driven primarily by landscape position and weather, but they didn't really interact. And so we always saw that the back slope was under yielding and the toe slope was yielding the highest among those 3 positions. So we saw pretty consistent spatial patterns from one year to the next. But that back slope was particularly sensitive to weather and rainfall. And then third, that cereal rye cover crop helped to decrease variability in yield by raising the corn yields in dry years, and especially on the back slope position. And so I just want to acknowledge the many different individuals who have helped with this research project, as well as our funding agencies, including the Kentucky Corn Growers Association. And we'll be glad to take questions if there are any.
So Hannah, I see a question in the chat from Carol Hinton asking about, is there a max or a minimum amount of cereal rye to plant in the cover crop?
So for this study, we used, I think it was about 65 pounds per acre. And that was working with our farmer cooperator who's used cover crops for many years and the rate that he has had success with. I think rye can be pretty flexible in that you could probably go a bit lower in the seeding rate and still achieve similar biomass levels, but obviously at some point, if you don't seed enough rye, you'll see a decline in biomass production. And then I think probably above about 65 pounds, you may obviously be just spending more on seed and not necessarily seeing that biomass increase. But I haven't looked specifically at different rye seeding rates. So we just went with kind of the recommendation from our farmer cooperator on that.
It seems like that 60-pound range has shaken out to be the best rate in terms of a little bit of insurance against a lower stand for some reason if you don't get full emergence, and it's not overly thick if everything comes up as well. That seems to be about the rate that most people are using when it comes to cereal rye. So that's a good question. And just as the agronomist, I look at those numbers on the different slopes, really, really good numbers. And I think if we know that the slopes are going to be much drier more frequently year to year than the other landscape positions, it sort of makes sense that we cut back on seeding rate on those slopes because our yield potential is not as high. And we know that driving corn populations can affect, you have higher populations where you have better yield potential, and you might as well have a lower population where you have less yield potential. So at least that's something else for me to think about. I may need to incorporate some of that data into the next time we update seeding rates. So really, really good information.